party are here. Hope you survived last night. I'll have the solutions posted soon, and bring them as soon as I can. All right. So let us continue. There is a homework assignment, and do your best to try and get started on it a little bit tonight. Look at it at least, so that we can productively have a problem session tomorrow. And as you remember, there's this room scheduling conflict. So we'll introduce the problems and discuss them a little bit from 10:15 to 11, and then hang out in the lobby, and I'll come around and talk to you and work with you there. Okay? All right. So last lecture, we had discussed that there are two different so-called pictures that one typically uses in different contexts to study dynamics in quantum mechanics. One is the Schrödinger picture, and in the Schrödinger picture, what we do is we dynamically evolve the state. So the state of the system evolves as a function of time according to the Schrödinger equation, which for a pure state is written like this, or more generally can be written like that. And the observables, the Hermitian operators that we use to calculate physical quantities are constant operators, unless they are functions of some classical parameters that themselves are explicit functions of time. Okay, but that's kind of an aside to them. In the Heisenberg picture, we flip things and we say the state is fixed, and the observables evolve in time, and they evolve according to the Heisenberg equations of motion. And the Heisenberg picture is useful in two important contexts. One, if we're only interested in the evolution of the expectation values of a few observables, then it's typically easier to use the Heisenberg picture, because you don't have to know the whole state, you just have to know how that particular expectation value evolves as a function of time. And if I'm thinking about things like multi-time correlation functions, which are also expectation values, then one typically works in the Heisenberg picture. So, typically in field theory, quantum field theory, and in condensed matter physics, it's almost exclusively done in the Heisenberg picture. Because, frankly, it's very hard to measure individual quantum systems in that case. So you're typically looking at average values anyway. Very hard to look at the probability of some particular event happening. So often it's done in the Heisenberg picture. The connection between these is through the unitary evolution. That's general. Whether I'm talking about the Heisenberg or the Schrödinger picture, there's a time evolution operator. And we take the initial conditions that whatever the Heisenberg operator is at time t equals 0 is what, the constant Schrödinger picture operator is. And whatever the Schrödinger picture state is at time t equals 0 is the same as what the constant, the fixed Heisenberg state is. So then they're connected at time t equals 0, and then they evolve in time. So the state evolves in this way, and in the Heisenberg picture, the operator evolves according to a unitary time evolution transformation, right? And by this connection, what that means is that any expectation value is the same whether I calculate it in the Schrodinger picture or the Heisenberg picture. So I plug in for the state this way or the operator this way, and I look at them, then they'll be the same. And that's why they are physically the same. There's just whether you shove the time dependence on the operator or shove the time dependence on the states. Either way. They have conceptual differences, but at the end of the day, it's matrix elements that carry the physical predictions. And so it doesn't matter which picture we use. All right? And one of the things about the Heisenberg picture is that it is much more similar to classical dynamics. In classical dynamics, the way we typically treat it, although there is a Schrodinger-like picture for classical dynamics, we just almost never use it. It's called the Liouville equation. It's like a Schrodinger picture for classical mechanics. We can talk about that at some point if you're interested. But typically we think about, well, you know, there are positions and momenta, which are the analogs of the observables, and they evolve according to Hamilton's equations of motion. And I got this backwards last lecture. I had the bracket. So this is the Poisson bracket. This way. And the Hamilton's equations of motion say if I want to see the time evolution of some observable, I take the Poisson bracket with the Hamiltonian. And the Poisson bracket is defined here. And it looks just like the Heisenberg equations of motion, except there's this IH bar thing going on. Okay? And so in particular, if I looked at, for example, how position and momentum evolve as a function of time, if I think about a particle moving in one spatial dimension in the presence of a potential, then I get the usual equations. This is that the momentum is related to velocity, and the change in momentum is given by the force, Newton's force. Okay? Right. Okay, any questions? Okay, so what we want to now discuss is, well, how do we treat this particular problem, the problem of mechanics, quantumly? Let's talk about quantum mechanics. Okay, we haven't done that yet. So, we're going to really now putting mechanics back in quantum mechanics. So, well, as we discussed, our hook for doing that is symmetries, okay? And so what we discussed is that momentum is the generator of translations in position. That follows from Noether's theorem, which says that if we have a translationally invariant system, if there's no difference in the system as a function of position in space, then momentum is conserved. Okay? And therefore, momentum is the generator of translations in position. Okay? So, now what that means is that we have if we're in the quantum world, now we have x and p canonical coordinates become observables. x hat and b hat. These are Hermitian operators. And there is a unitary representation of translations in space or position. Now, for the moment, I'm going to restrict my attention to one spatial dimension. We'll generalize that a little bit later. The subtleties involved there when we think about 3 dimensions or multi-dimensions. Let's just think about 1D here. So these translations in position is a Lie group over the real line, okay? And so this unitary representation is the following. Let's say T is a unitary operator. And to say that is a representation of translations in time, it says that if I do a unitary translation on the position operator, where this particular element of the group, oops, this is a 1D, sorry. If I, hold on one moment, if I translate this by some amount, then what I should get is this, yeah. And this is really means x0 times the identity, but we will write that in typically. So this is saying that on this side, I do a unitary transformation on the position operator, and its action is to translate position by that amount. Okay? Okay, so that's what we want. And since momentum is the generator of that action, then we can write down what this translation operator is in the same way, using the same technique that we used in thinking about time translations. And the way we did that, it was to think about translations that are near identity. So just a differential translation. So near identity transformation see if I translate for a little differential dt. Well, this is the identity, and then we said that the generator had to be anti-Hermitian, so we factor out a minus I. There's some operator I'll call k dx. Okay? Oh, actually, let me write it out. We know that it's proportional to momentum. So momentum is the generator of time, of space translations. So my near identity translation operator is the identity and then a small amount proportional to dt times an anti-Hermitian operator. That anti-Hermitian operator is got to be plus or minus I. That's just by convention. Take it minus I times momentum operator. And then there's some constant, alpha. Now this has to be dimension. This whole thing has to be dimensionless. Has no dimensions. It's just an operator. If this is the identity operator, the identity operator has no dimensions. So this whole thing has to have no dimensions. Right? So that means that the units of this proportionality constant is 1 over the units of position times momentum. Right? So that this thing. And that is action. It's another way of writing action in constant physics. And it's the same constant. Well, range 1. So our near identity translation operator is thus, I mean, this can't really derive that it's h bar It's just that is the consistent way, as we'll come to a little bit later, why h bar is the units that ever come into quantum mechanics. It's a way of, in some sense, translating physical stuff into distinguishable states. It tells me how many, what's the dimension of Hilbert space in some sense. It's a kind of way in which we coarse-grain phase space. But with all of that said, let's just plug it in and say this is the near identity translation. Okay? And this has to act, if I act this unitarily, translate the position operator, it should translate by that. Okay? So let's plug that in. That's equal to the identity. The conjugate of this is plus I over h bar. This is a Hermitian operator, so p dagger is p times x times the identity minus I over h bar p times the x. Okay, this is a differential, so we keep only things to first order. The x squared is 0 as a differential, so we'll keep only the those terms. And what do I get? I get minus I over h bar x times p minus p times x dx. I don't know if the identity should be x. Right? Et voila! I love saying that. What we see over here is, in order for this to be the case, this whole thing, well, has to be 1. Right? Because this equals that. And thus, we see, in order for to say that momentum is the generator of translations in position, it must be the case that the lead bracket, which is the commutator, satisfies the following. X times p minus p times x is the commutator is equal to h bar over minus I, which is I h bar. Yay! So this commutator is nothing but the statement that momentum is the generator of translations. It has to have that computational condition. If they commute it, well, then momentum would do nothing to position. Okay. Okay, cool. So now we can also say, we can write down the translation operator in position for a, not just for a differential, but for an arbitrary finite translation. So if I translate by an amount, say x naught, again, I can break that, I can take the limit of little differentials. So I'm going to write this in terms of I over h bar p, and then x over n. And then I do that n times. Okay? So this is my near identity, because n is very, very big. This goes to infinity, but then I do it, this is the same thing. And this is e to the minus I over h bar px. Okay? So that's the translation by a finite amount x, and if x becomes a differential, when I expand this as a power series, I get that. Okay? Now, just to be pedantic, because that's my nature, let's just show that this is all self-consistent by using Baker-Campbell-Hausdorff, or some version of that. So let's look explicitly at that. Okay? This is e to the plus I over h bar t hat x naught, x hat e to the minus I over h bar t hat x naught. Right? And what we wrote down last time is that we can do this transformation through multiple commutators, right? So aside up here, remember we had e to the b, e to the a, a e to the minus b was equal to the sum n equals 0 to infinity, 1 over n factorial, the multiple commutators of b with a n times. Okay? Where this if I, what that means is where 0 is b. I'm sorry, a. And then do it one time, it's b with a. Do it two times, it's b with a. Do it three times, it's b with a, etc. So let's do it. What's a and what's b in this case? Well, here's a and here's b. Right? It has this form. And thus, this is equal to, the first term is x. The second term is the 1 over 1 factorial is 1, plus the commutator of this with this, plus the next term is a half the commutator of this with that again, and then etc. Right? Well, yeah, it's still correct. Yes, this is correct. So this guy is what? Well, there's a constant. We bring that out. I over h bar, the commutator of p with x. And the commutator of p with x is minus the commutator. There's an x0 in there. Thank you so much. Let's put it over here. And the commutator of p with x is minus I h bar. Right? So minus I, that becomes 1. Okay? So this is to 1. Now, as he suggested, the rest of these terms I can throw out. Why? Because the magic of these particular operators is that their commutator is a constant. It's proportional to an identity operator. And thus it commutes with everything. It's alone. So it commutes with that, it commutes with all these other terms are 0. Because this is a constant. And the constant, or the identity, commutes with everything. Et voila, once again I get to say that this is equal to what we want it to be. So it works. All right then. So let's now show the Heisenberg equations of motion for x and p when I have a Hamiltonian of the form that I wrote down over there for classical mechanics. So the Hamiltonian for a particle moving in 1D with a potential V. The Hamiltonian operator now is the kinetic energy operator and the potential operator, which of course is the potential operator as a function of x hat. And we know now what this means. If it's a function of an operator, we know what that means. So now, let us write the Heisenberg equations of motion. So let's look at the derivative of x hat with respect to time. That's equal to I over h bar, right, minus I over h bar x to h. One of the forms that we have over there in the front board. Okay. So this is equal to what? Well, plugging that in, I get minus I over h bar, the commutator with the kinetic energy term, and the commutator with the potential energy term. Okay. Of course, this is 0 because x commutes with any function of x, right? And now what about this? Well, we got to use the old product rule in that case. So this is a little commutology. Let's just write it out just to remind ourselves how that goes. So just factor out all the constants and let's look at this. And what do? Well, I have to take, remember, put a little aside over here. The commutator of A with the product of B and C is A with B times C plus B A with C. We should prove that at some point, or we just remember it, and we better start remembering. Okay, so now we do that. So this is the two things, so I get minus I over 2h bar m times the commutator of x with p times p plus p times the commutator of times that again. Because in this case, both b and c are the same. So I just did it twice. Think about this, p times p, right? And this are both equal to IH bar. So this thus is equal to p hat. Right? Yay. So what we have here is that we have this, and similarly, and you'll do this for homework, the time derivative of the momentum operator with respect to time, which is minus I over h bar, the commutator of p with h, which is the commutator of p with the potential operator. If you go through those details, you will find that this is equal to this. Homework to come. Okay, so this looks like that. I mean, it looks exactly like classical mechanics, doesn't it? I mean, these are Hamilton's equations. So what does it say? So this is often stated as Ehrenfest's theorem. Okay. Ehrenfest's theorem. It would help if he spells it. Let me have a method written down. Dyslexia comes comes to bear. Because it's understood. Ampere's theorem says loosely that mean values in quantum mechanics follow the classical trajectories. This is how it's often stated. That is to say, if I let x equal the expected value of x and p equal the expected value of p, that dx dt is p over m, and dp dt is equal to minus value at x. So it looks like I just recover classical dynamics as long as I just follow the center of the wave, the mean value. Now, this is wrong. Why? Why is it wrong? I mean, it looks like that's true. There's a very subtle point here. Let's actually take the expectation value of these equations. Okay? So what we have is the x dt is p over m, which implies that. Well, that's cool. That's exactly this. If I replace this by the mean value, I get that. That's fine. However, if I look at the second equation, that says if I take the expectation value of both sides by shoving on Rosen-Ketz, then I get that the rate of change of the mean value of momentum is equal to minus the that. But this does not generally equal that. Sometimes we'll see that that's true, but in general, no. For example, suppose I have a coordinate potential. Okay? So suppose the potential as a function of x was some fourth power. Okay? Then the force on the particle is that, right? Minus, right? So now, what is the expected value of the force? Well, it's this. But this does not equal that.
Should it be 3?
It should be. No, what am I talking about? No, that's right. All right. No, here, sorry, it should be 3. Indeed. Doesn't equal that either. Right? it would only be true if the particle was extremely well localized, such that the fluctuations were negligible. So only if delta x, the uncertainty, the fluctuation, or let's say it this way, is much, much less than variations in V. So if the particle is extremely well localized compared to the way in which the potential changed, then it doesn't see that. But if the particle is delocalized and samples different parts of the potential, it experiences different forces in some sense, or it experiences coherent superpositions of different forces. So it is not correct to say that a particle's mean value, its wave packet, just follows the classical trajectory in general. Now, there are some cases where that's true. Suppose I had a quadratic potential. It's called the harmonic oscillator. Right? Then in this case, and the mean value of this is the same thing. For that case, this is true. So if I have a quadratic potential or a linear potential, then yeah. So in a harmonic oscillator, the wave packet's mean value follows the classical trajectory, but in other ones, they don't. And in fact, if classically the system is chaotic, then the wave packet will spread incredibly fast. And so that means that even if at the initial times I had the particle well localized, at very short times it's going to be extremely delocalized. And it's what we call the quantum break time. The time it takes for the particle to no longer follow the classical trajectories breaks at a time that's very short if the system is chaotic. In fact, there was an interesting paradox that was posed by Wojciech Zurek in thinking about this and thinking about one of the moons of Saturn, which has a chaotic orbit, the Hyperion. Is that Saturn or Jupiter? When you're trying to never, it's embarrassing. And you ask the question, how long would it take before the trajectory of this moon is no longer described by Newton's equations? Even though it's the damn moon, which is as macroscopic as you can do that. And it's actually very short time. I tried to look it up at that time.
Are you thinking of Mercury's orbit?
No, I'm talking about, it's one of the moons of, in this case, it's Hyperion. But, the same, you could do the same. I don't think Mercury's orbit is chaotic, is it?
Mercury orbit takes on some belts up, including belts to the sun.
Yeah, but it's not chaotic. This is about chaos. Now, that's a little bit of a paradox, because we really don't expect that we need quantum dynamics to describe the trajectory of the moon. So there is this question about the emergence of classical phenomena. So the resolution to that paradox is, again, that the moon, in this case, the moon of Saturn, is not a closed quantum system. It's an open quantum system, constantly being interacted with. And so the interference between different trajectories that give us the quantum don't interfere anymore. They decohere, and decoherence rescues the moon once again. All right, very good. Now, let's talk about things from the point of view of the Schrödinger picture. of course, true Schrodinger orbiting. Let's talk about the state space. Hilbert space. So, we have position and momentum operators. We have position and momentum representations. So, X and P are Hermitian operators, thus we can look for their eigenvectors. And because we're talking about this continuous symmetry of time translations, these eigenvalues are real numbers that are continuous. So these are the eigenvectors. And these are the eigenvalues. And these eigenvectors and eigenvalues form a resolution of the identity. Now, because they are continuous, we don't just sum, we integrate. Okay? So the resolution of the identity now becomes the following. Integrate over all the position eigenstates. It's a dummy variable, we love the x0, from minus infinity to infinity. That's the identity. And similarly, for the momentum, now things get quite messy here and complicated. There's a whole lot of rigor here that we'll touch on, but we're going to sweep a good part of it under the rug. But let me just say at least one word here. Firstly, if we look at this expression over here, x has units. It's units of length. And this is dimensionless, right? Similarly here, this has units of momentum, mass times velocity, and this is dimensionless. Which means that these kets or bras have units in this case. Okay, so this thing has the dimensions of 1 over length. It's a density, a linear density. And this thing has the dimensions of 1 over momentum. It's a momentum density. Okay. All right. Well, given that, we can write down, we have a state. Let's talk about pure states in Hilbert space. We can write down a position representation. How do we do that? Well, if we have a basis, a resolution of the identity, we know how to do it. We just write the state And this is our expansion coefficient of the state in that basis, right? But now it's a continuous variable basis. And this is called the wave function. So the wave function is nothing but the representation of the state in position. Okay? Now, what are the possible allowed wave functions in the Hilbert space? Well, what we must be the case is that this thing we should be able to normalize. So if this is going to be a probability distribution, this must be normalizable. And typically, we will set this equal to 1. Okay. So, in this case, if it were a, if this were a discrete basis, we would write the normalization like this, right? And that, of course, is equal to the state in whatever the basis is. But now we have this continuous basis. So let's plug that in. And that's just equal to this. And that's got to be equal to 1. So the allowed states in Hilbert space are the ones such that when I integrate them, square their magnitude and integrate them over the whole real line, I get a finite number, and I set it equal to 1. So this Hilbert space has a technical name. That Hilbert space is called L2 over R. That Hilbert space is the space of square normalizable functions. And of course, how do we interpret the wave function? Well, one thing we see just from our general theory of measurement. So, when we interpret the wave function, so what we have here is that we have a resolution of the identity. Which is in terms of, it is a positive operator value measure. Here it is. Now it really is a measure, as thought about as a measure on, as an integral measure. This is the projector onto the range x to x plus dx. And then I sum up all those little slices. Okay? So what that means is that the Born rule tells me that this is my projector and this is my state. And this is then dx psi star psi. Right? That this is the probability to find in a projective measurement the particle in the range x to x plus dx. So, what this tells us is that the magnitude of the probability amplitude in the position representation squared, aka psi star psi, is what we call the probability density. So when we have our random variable that we're measuring, in this case position, is a continuous variable, we can't talk about the probability to be at a point, because that's a set of measure 0. We can only talk about the probability to be within some, differential range. Okay. So this is the probability density. Right. Okay. Moreover, let's say, what else can we say about the position representation? I want to say, what about translation operator? How does it act? So let's say that we have some psi, and we look at psi of x, the wave function. Okay? And let's suppose it were the case, it doesn't really matter, that this psi of x was a wave packet localized at the origin, centered at the origin. Now let's ask what the translation operator, should do. If I look at, let's call psi prime, let's translate it by an amount x naught. Okay? And what is the wave function now of this, which is equal to this? Well, it's just the guy that's translated by x naught. Okay? So if this should be the same shape. So imagine that. You're very good at imagining my drawings. If this is psi of x, what is this? Psi of x minus x naught. Right? So with that minus sign, because with its value at the origin is the same as its value at x naught. Okay. So this function is psi of x minus x naught, which means that this has to be x minus x naught. So what we have here is that the translation operator acting to the left is x minus x naught. Now I can take the adjoint of this whole thing, and that becomes t dagger of x naught acting on x is x minus x naught. Right? But this is unitary. And so t dagger is t inverse. But the inverse is just translated by minus x. So this is a very long-winded way of saying that the action of the translation operator on the eigenket is that. All right. Now, of course, we have another representation that we just discussed because we have position and momentum. So I have the momentum representation. That's to say, if I wanted to, I could write the resolution of the identity in terms of the momentum basis, in which case I have a representation which I'll call psi tilde. So this psi tilde, the momentum space wave function, is nothing more than the probability amplitude in the position eigenspace. I'm sorry, the momentum eigenspace. All right. And of course, we can equally well look at the normalization the norm squared of the state in momentum space. So the momentum space wave function is normalized in this way. And the same interpretation holds. This is the momentum space probability density. That is to say that the probability to find the particle with momentum in the range p to p plus dp is dp times momentum space wave function squared. Okay. All right, so what we have been studying, though, for the last month is that we can always transform between any representation in one basis and the representation in another basis via a unitary transformation. And that unitary transformation has a name here. It's called the Fourier transform. But it's just an example of what we've been doing in terms of linear vector spaces. So let's do it. If I have the position space representation, I can get to the momentum space representation. So if let's say I want to get to the momentum space representation. Okay, that's the momentum space wave function. Well, how do I do it? I insert a resolution of the identity in the new basis. And the new basis, in this case, is x. this is just another way of writing a unitary transformation. This is like my column vector, and this is like my elements of my unitary matrix. I go from this column vector to that column vector. But now, it's not matrix multiplication, it's the integral. Because these are not discrete numbers, it's continual. And so this is my change of basis unitary. Similarly, we could do the inverse. We can go from momentum space to position space, and by exactly the same. Now it's the inverse of this, and the inverse of this is the adjoint, and the adjoint of that is the conjugate, so that's this. Oh, I'm sorry. Yes, thank you. Thanks. Absolutely. Okay. So now, what is the value of this that's calculated? So to do that, what I'm going to do is say, let's consider the norm of the vector, norm squared, which I could write as an integral over the square of the probability amplitude in momentum space, by light, for example. Let's plug that in. Okay. So that's equal to the integral over all momenta. And then I'm going to write that squared. So I multiply this by its complex conjugate. So I have two integrals over x, and they're two different integrals, so I have to have two different dummy variables. An integral over x, and an integral over x prime. Okay? Oh, yeah. I'm sorry. Okay. I realized where I was going with this, but I left out one important step. So let me just write this down and then I'll explain what I meant to do. So this is equal to some px and then the conjugate, and then there's a prime on one of these guys. And then this. Okay. And just plug that in. Which is backwards. Yeah. That's right. Okay. But hold that thought. I forgot one step. We could draw it in many ways, but I wanted to draw it in one side. Let's consider this up. Okay. That's one of our guys over here. Well, according to what we just expressed before, this guy is equal to x is translating from x equals 0 by some amount of x, right? And this is p. It's another way of writing it. But the translation operator, which has now been erased, was the exponentiation of something. E to the minus I over h bar p hat x. Now I ask you, what is the action of this guy on this? P hat operator act on this.
P hat is equal to the number P.
Right? We can just replace it because this is an eigenvector of P and it doesn't matter, it's in the exponent. So that becomes a number. E to the minus I over h bar P x. And this is just some number. N, independent of x. And then the other guy is just the conjugate of that. Which we take to be real. We always have a conventional overall phase we can choose, and we'll choose it to be real. Okay? So, now I can go and plug that in. Okay. We don't know what this n is here, but let's plug it in. So now I have n squared. I have the integral. I'll put these integrals, take these guys, reverse the order of integration, which using physics we always do, unless we have to worry about it. Integral over p. E to the I. What do I have here? Px, right. P over h bar x minus x prime. Okay, what do we do now? Well, this integral is something that I'm sure you've seen. If I ask you, what is the integral from minus infinity to infinity of some, say, p e to the I k x minus x prime, what is that? It's in the delta function, right? It's got some factors in it. And if I write it, that's right. This is equal to 2 pi times the delta function evaluated. Okay, never mind. Let me, sorry. Get rid of these damn units. Let me try again. Let's say we integrate over some variable k. Then I can write this down. This is this. For sure. So this, where this is a Dirac delta function. Okay. So now, this integral, if I divide by h bar over here and multiply by h bar over here, then I can call this k, and I get 2 pi delta x minus x. When I integrate over the delta function, x prime, that replaces, wherever I see an x prime, gets an x. So this becomes 2 pi h bar n squared, the integral from minus infinity to infinity dx integral squared, which is equal to 1. Okay, because this all the way back here was supposed to be the norm of the wave function. But this is also equal to 1. So that tells me how I should normalize this. It tells me that I'm going to choose n to be equal to 1 over the square root of 2 pi. Okay, so we now have the relationship between the position and momentum space wave functions, and of course, it's nothing but the Fourier transform. And you should always think of a Fourier transform as nothing but a change of basis. That's how you should think about it. We're going to have two linear representations, one in terms of position or momentum or time and frequency. Just a change of basis. So we have the Fourier transform says the momentum space wave function is the integral over all positions e to the plus I dx over hr psi of x with a square root of 2 pi hr. And the momentum and the position space wave function is the inverse Fourier transform. In other words, in order to get the momentum space wave function, I have to project the state onto the position eigenstates. That's what I'm doing here, right? So momentum space wave function, momentum space eigenstates. That's what this is saying. Plugging in the x. Or the position space wave function I project onto the position eigenstates, this expressed in momentum space. All right. Now, there is one important fact here which we kind of sloughed over. So, position and momentum space eigenvectors are not L2R. They're not in the Hilbert space. What do I mean by that? Well, let's look at, let's say, suppose the state of the system were a position eigenstate. Let's say it were. Say this thing is supposed to be something in the Hilbert space. It's got to be the case that for its momentum space wave function, for example, should be 1, right? Because if it's in the space, it's normalized. Let's try to do that. Well, according to this, that's equal to this, which is, you know, we put this factor in there, and that was equal to e to the minus I px over h bar, right? There's nothing there. So let's plug that in. Square that, so from minus infinity to infinity. The integral of this thing, the norm of the square of that, 1 over 2 pi. And the square of that is, what's the magnitude squared of this? 1, right? And so that is infinity. So that it's not possible. So the same thing is true for momentum. These things are not square normalizable. They're not in the Hilbert space. Okay? So it's there's a whole sophisticated structure that we're just touching our toes into here about when we talk about Hilbert spaces with infinite dimensions about allowed states, non-allowed states, bounded operators, unbounded operators. For the most part, we get away with this in physics by dealing with things like delta functions. That's where I bury this. Delta function, of course, is not a real function. It's what you call a tempered distribution. But formally speaking, X and P are not in the Hilbert space. Now their duals exist because I can talk about the bras because it gives me a perfectly fine representation. But the kets don't. One way, the last thing I would say about this, what this means is that position and momentum eigenvectors are unphysical. There is no preparation that can prepare the system in an eigenstate of position or an eigenstate of momentum. Why? Because that would take an infinite amount of energy. If you have a position eigenstate, it has a spread, uncertain momentum to all possible momentum. It has an infinite amount of energy. Okay? You can never localize something to a point. You can localize it as close as you want, but not to a point. So it's no worry mathematically that these things are not in the Hilbert space. And the same thing for momentum, because it's an unphysical state. Which is why we can never ask the question, what is the probability to find a particle at position X? Because that would mean find it at that point. It would take infinite precision to do so. We could say to within, some digits of precision, some small range, as small as we like, but never at a point. Yeah.
So are the different cats of X and P's, they're just all the different direct distributions along every point? Or
right. So let's ask this question. We'll conclude this. Suppose I have the state of the system, if I wanted to write it, formally speaking, as let's say it's localized at some position x naught. And I ask, well, what is the wave function associated with this? Well, that's this. And this is this. Okay? So we can write it down formally as a delta function, localized at x naught. But it's not a good function, because if I square it, first of all, it blows up. It's when its argument is 0. And moreover, if you try to square it and integrate it, you get infinity. It's not normalizable. So it's an unphysical state. There's no such state. We can't prepare the state. We prepare something that approaches it and can make a Gaussian wave packet with a width that is extremely narrow, which limits to a delta function, but it never is exactly with 0. All right, we will continue this and solve the particle in the box. It is much more similar to classical dynamics. In classical dynamics, the way we typically treat it, although there is a Schrodinger-like picture for classical dynamics, we just almost never use it. It's called the Liouville equation. It's like a Schrodinger picture for classical mechanics. We can talk about that at some point if you're interested. But typically we think about, well, you know, there are positions and momenta, which are the analogs of the observables, and they evolve according to Hamilton's equations of motion. And I got this backwards last lecture. I had the bracket. So this is the Poisson bracket. This way. And the Hamilton's equations of motion say if I want to see the time evolution of some observable, I take the Poisson bracket with the Hamiltonian. And the Poisson bracket is defined here. And it looks just like the Heisenberg equations of motion, except there's this IH bar thing going on. Okay? And so in particular, if I looked at, for example, how position and momentum evolve as a function of time, if I think about a particle moving in one spatial dimension in the presence of a potential, then I get the usual equations. This is that the momentum is related to velocity, and the change in momentum is given by the force, Newton's force. Okay? Right. Okay, any questions? Okay, so what we want to now discuss is, well, how do we treat this particular problem, the problem of mechanics, quantumly? Let's talk about quantum mechanics. Okay, we haven't done that yet. So, we're going to really now putting mechanics back in quantum mechanics. So, well, as we discussed, our hook for doing that is symmetries. Okay? And so what we discussed is that momentum is the generator of translations in position. That follows from Noether's theorem, which says that if we have a translationally invariant system, if there's no difference in the system as a function of position in space, then momentum is conserved. Okay? And therefore, momentum is the generator of translations in position. Okay? So, now what that means is that we have if we're in the quantum world, now we have x and p canonical coordinates become observables. X hat and p hat. These are Hermitian operators. And there is a unitary representation of translations in space or in position. Now, for the moment, I'm going to restrict my attention to one spatial dimension. We'll generalize that a little bit later. The subtleties involved there when we think about 3 dimensions or multi-dimensions. Let's just think about 1D here. So these translations in position is a Lie group over the real line, okay? And so this unitary representation is the following. Let's say T is a unitary operator. And to say that is a representation of translations in time, it says that if I do a unitary translation on the position operator, where this particular element of the group, oops, this is a 1D, sorry. If I, hold on one moment, if I translate this by some amount, then what I should get is this. Yeah. So, and this is really means x0 times the identity, but we will write that in typically. So this is saying that on this side, I do a unitary transformation on the position operator, and its action is to translate position by that amount. Okay? Okay, so that's what we want. And since momentum is the generator of that action, then we can write down what this translation operator is in the same way, using the same technique that we used in thinking about time translations. And the way we did that, it was to think about translations that are near identity. So just a differential translation. So near identity transformation. See, if I translate for a little differential dt, well, this is the identity, and then we said that the generator had to be anti-Hermitian, so we factor out a minus I. There's some operator I'll call k dx. Okay? Oh, actually, let me write it out. We know that it's proportional to momentum. So momentum is the generator of time, of space translations. So my near identity translation operator is the identity and then a small amount proportional to dt times an anti-Hermitian operator. That anti-Hermitian operator is got to be plus or minus I. That's just by convention. You take it minus I times momentum operator. And then there's some constant, alpha. Now this has to be dimension. This whole thing has to be dimensionless. Has no dimensions. It's just an operator. If this is the identity operator, the identity operator has no dimensions. So this whole thing has to have no dimensions. Right? So that means that the units of this proportionality constant is 1 over the units of position times momentum. Right? So that this thing. And that is action. It's another way of writing action in constant physics. And it's the same constant. Well, range 1. So our near identity translation operator is thus, I mean, this can't really derive that it's h bar. It's just that is the consistent way, as we'll come to a little bit later, why h bar is the units that ever come into quantum mechanics. It's a way of, in some sense, translating, well, the hardy are here. Hope you survive. I have the solutions posted soon, and bring them as soon as I can. All right. So let us continue. There is a homework assignment, and you've asked to try and get started on it a little bit tonight. Look at it at least, so that we can productively have a problem session tomorrow. And as you remember, there's this room scheduling conflict. So we'll introduce the problems and discuss them a little bit from 10:15 to 11, and hang out in the lobby, and I'll come around and talk to you and with you there. Okay? All right. So Last lecture, we had discussed that there are two different so-called pictures that one typically uses in different contexts to study dynamics in quantum mechanics. One is the Schrödinger picture, and in the Schrödinger picture, what we do is we dynamically evolve the state. So the state of the system evolves as a function of time according to the Schrödinger equation, which for a pure state is written like this, or more generally can be written like that. And the observables, the Hermitian operators that we use to calculate physical quantities are constant operators, unless they are functions of some classical parameters that themselves are explicit functions of time. Okay, but that's kind of an aside to them. In the Heisenberg picture, we flip things and we say the state is fixed and the observables evolve in time, and they evolve according to the Heisenberg equations of motion. And the Heisenberg picture is useful in two important contexts. One, if we're only interested in the evolution of the expectation values of a few observables, then it's typically easier to use the Heisenberg picture, because you don't have to know the whole state, you just have to know how that particular expectation value evolves as a function of time. And if I'm thinking about things like multi-time correlation functions, which are also expectation values, then one typically works in the Heisenberg picture. So, typically in field theory, quantum field theory, and in condensed matter physics, it's almost exclusively done in the Heisenberg picture. Because, frankly, it's very hard to measure individual quantum systems in that case. So you're typically looking at average values anyway. Very hard to look at the probability of some particular event happening. So often it's done in the Heisenberg picture. The connection between these is through the unitary evolution. That's general. Whether I'm talking about the Heisenberg or the Schrödinger picture, there's a time evolution operator. And we take it the initial conditions that whatever the Heisenberg operator is at time t equals 0 is what, the constant Schrödinger picture operator is. And whatever the Schrödinger picture state is at time t equals 0 is the same as what that constant, the fixed Heisenberg state is. So then they're connected at time t equals 0, and then they evolve in time. So the state evolves in this way, and in the Heisenberg picture, the operator evolves according to a unitary time evolution transformation, right? And by this connection, what that means is that any expectation value is the same whether I calculate it in the Schrödinger picture or the Heisenberg picture. So I plug in for the state this way or the operator this way, and I look at them, then they'll be the same. And that's why they are physically the same. There's just whether you shove the time dependence on the operator or shove the time dependence on the states. Either way. They have conceptual differences, but at the end of the day, it's matrix elements that carry the physical predictions. And so it doesn't matter which picture we use. All right? And one of the things about the Heisenberg picture is that